Factor groups.
Woohoo!
Very exciting. Okay, so factor groups. Factor groups, that's what we were doing. So what are they good for?
Absolutely nothing. Yeah.
Oh, they are good. So, like, what we did was we have this normal subgroup, and you do the cosets, okay? And so you have like 3 groups. Yeah, you have the whole group G. You have a normal subgroup N. Okay, that does something on some elements. And then there are the cosets.
Yeah.
And kind of what happens among the cosets is this factor group. So that's G / N. So, you know, so it's like, you know, you have to, so these cosets are now parts of they're now elements of a group. And something happens on those cosets. It's like a different group again. So in some sense, these two things, the normal subgroup and the factor group, tell us everything about the group. Yes. Well, in what sense? Well, in many different senses, but one of them is that if you know what the normal subgroup is, and if you know what the factor group is, then up to isomorphism, there is only one group that does the same thing. So if you want to study all finite groups, for example, as you will want to, with Killian in a few weeks' time, then one way of approaching it, well, for non-abelian groups in particular, is that you're looking at normal subgroups of them and kind of the structure that you get from the factor groups. But just explains everything in every finite group. And that's the idea of having factor groups. Then there was this remark, and I've given you the remark typed up. The remark was, well, we did factor groups using normal subgroups, but is there a different way? Is there another way of doing it? We didn't know anything about it. Do know about normal subgroups. But, and the remark is, no, there isn't. We need normal subgroups. So there is no way of doing it without normal subgroups. Okay? And the proof why we need normal subgroups is started here. Okay. Now, what did we have as the first thing was that we needed, well, what was a factor group? Well, you split the group into some bits. Okay? They were the cosets of the normal subgroup. But if you split it in any way you want, for it to be able to put some kind of a group structure on it, as a factor group, we had this thing that if you have 2 elements, A and A dash, from the same parts of the partition, and then you have B and B dash, which also are in the same subset, then you want, if you do the products, you want, no matter whether you pick A or A and B or A dash and B dash, you want them to be in the same subset, because otherwise you couldn't use multiplication or the group operation in G. You couldn't use it to define an operation on the sets, because if it depended, like if I take A and B, I end up here. If I take A dash and B dash, I end up here. What can I do? Well, I can't say what the product of these two sets is. So I really need that if I take, no matter which element I pick here, no matter which element I pick here, the products all have to sit in this set, or in one set, but they can't jump from set to set. Okay, that's kind of a necessary condition. Otherwise, you don't know how to define the operation on the subsets. And if you have a relation which satisfies this, and the partition is equivalent to an equivalence relation, and an equivalence relation which satisfies that has this property is called a congruence. Okay. Now, we want to prove that the congruence kind of always has to come from a normal subgroup. So the first step is this exercise, which already has been exercised in the handout, so I'm not going to do it. But the second step was to prove that if you look at where the identity, so the identity is in one of these classes, the equivalence. So the class of the identity is a subgroup. So if I look at all the elements that are in the same class as the identity, that forms a subgroup of G. Okay, and we proved it, I think. Is there anything missing? If I have G, which is in the same subset as the identity, then its inverse is also in the same subset as the identity. And if I have G and H, then their product is also in the same subset. That's what we did last week. Okay? Third thing that we want is that N is a normal subgroup. So why is this? Well, we want to show that for any G we want. We do G and G inverse, that's a subset of N. That's one of the equivalent conditions for a subgroup to be normal. So take some G in G and N in N. Now, what do we have? We have that G is in the same subset as G, and N is in the same subset as E because N is in N. And therefore, Gn is in the same subset as Ge because it's a congruence. Okay? So if we times left-hand side times the other elements, we always get in the same subset. And also G inverse is in the congruence with itself. So if we do G and G inverse, that's in the congruence with G inverse, which is nothing else than the identity. And if something is in a congruence with the identity, that means that it's exactly the same thing as saying that it's in it. Okay, so and that is true for any n big N. So this is a subset. And the thing number 4 that we want to do is to show that all the equivalence classes of tilde are actually cosets of N. So the tilde equivalence classes are exactly all the cosets of N. So the first thing is we want that if you look at the equivalence class that contains G, that this is a subset of the coset of G, okay, for any G. So first I want to prove that if I look at in the partition that we have here, given by the tilde, if I look at any one of these bits here, it's a subset of the coset of any element in there. So there's a G. So its coset could be larger, possibly, but certainly the whole equivalence class is in the coset. Now, how does one do this? So if I look at any H, which is in this subset, that means that H tilde G, because that's how the equivalence class is defined. Therefore, if I do G inverse H, that's equivalent to G inverse G, which is the identity. Okay, so therefore, because G inverse H is equivalent to the identity, that means that it's in N. And therefore, if I times it by G, that's in Gn. But this is nothing else than H. So that proves A. Okay. And the second thing I want is that the coset of G is a subset of the equivalence class of G. So if I take, so again, I take any H in the coset. Well, what does it mean that H is in the coset? It means that I can write H as Gn for some element of some element of N. Well, what does this mean? What does it mean that N is in N? Well, that means that N is the same class as E, and therefore Gn is in the same class as Ge, and therefore H is in the same class as G, and therefore H is in the equivalence class of G. So that proves the other inclusion. So now we know that any coset of N is exactly equal to the subset that contains that element, and therefore the partition into, we have two partitions, right? We have one which is given by tilde, and we have another partition which is the partition into the cosets of N, and they necessarily, because of these two, they have to be the same partition. So that's basically it. The partition of G into the coset of N, and the partition of G into the equivalence classes are one on the same partition. So that's the proof. That was a coursework question last year. It's kind of an exercise as well when you look at it. But the moral of this is that really normal subgroups are the thing we need for factor groups, which is the thing we need for studying the structure of groups. And that's that. And what else? So remember this again. 1 killion tells you that the kernel of a homomorphism is a normal subgroup. Okay. Now you know. Now you don't know what that means, of course, but just keep it as a pointer into the future. And when you know what the kernel of a homomorphism is, then this will kind of come back to haunt you. Is everybody excited?
Yes, but not twice.
No.
Maybe that's not later. That's what it's not.
Is that exciting?
Yeah.
Is it?
No, we're playing that. That's what it is. But,
Okay. Anyway, so right, so well, I started by saying what we need factor groups for, are normal subgroups. Okay, so we kind of from looking at subgroups, sorry, factor groups and normal subgroups, we can analyze the structure of any finite group, and even infinite groups, but finite groups. But there have to be some basic building blocks that you start with and that you're using and that you build just to home. And you can build any group from, and they're called a simple group. So a simple group is one that doesn't have any normal subgroups. Well, that of course is nonsense because every group has some normal subgroups. Trivial ones, but other than just the identity and itself. So that's called non-trivial, indeed. So there is a big catalog of finite simple groups. It's called the classification of finite simple groups. And there are some small groups in it, and there are also some big groups in it, like the monster group. But we won't do the monster group. We will do an example. So the alternating group is simple.
Yeah.
The proof takes 2 hours, so let's start.
2.
So first we look at some things in the alternating.
All these are just the numbers that we need to prove.
Yeah. So the alternating group, AN, is generated by 3 cycles.
That's the box.
So that's a really simple one. What are the elements of AN?
All the even permutations.
Yes, they're all the even permutations
Of like and no. Yeah.
of M. Yeah.
Oh wait, not all.
So now we know that N consists of all the even permutations.
I always think of it as an all
Okay. What is now we know that you can write any even permutation as the product of an even number of transpositions. Is that right?
Yeah.
So any element of AN is the product of an even number of transpositions Now, if I look at 2 transpositions, there are 3 possible cases. Either the 2 transpositions are exactly the same, or they share one element, or they're disjoint. Okay? If I take 2 transpositions, then exactly one of these things happens. A, B, C, D are all different. So this is just the identity. A, B, A, C is, yeah. What do you know? And ABCD is ACB, ACD. Okay, you can check it. It works. Just checked it. Okay? Any questions? Good. So the product of two transpositions can be written as the product of 3 cycles, either 0 3 cycles, or 1 3 cycle, or 2 3 cycles. So when I take the whole product of an even number of transpositions, I can pair them up and replace them with 3 cycles, and I get that. Therefore, any element of AN is the product of 3 cycles. Okay? So there's not a lot. They're not 10.8 and a half. If I take n, which is greater than or equal to 3, and I take any ij, I fix them, okay? So I pick my favorite 2 numbers from the set from 1 to n. They're different. And I just look at the 3 cycles that start ij. So I look at all the 3 cycles where I is I, and j is j, and a is anything. So a is 1, 2, up to n, but a is not allowed to be I or j. So that's a set. And if I look at all the elements that this set generates, the subgroup that is generated by these elements is the whole AN. What does this mean? Well, lemma 10.8. What did it say? It said that if I take all 3 cycles and take all their possible products, I'll get all the elements of AN. This lemma says, well, I actually don't need all 3 cycles. I can fix 2 elements, ij, and I'm only changing the last one into 3 cycles. And when I'm multiplying them together, I still get all the elements of AN. Okay? Well, why is that? First, can I get any 3 cycles? So of course I can get all the 3 cycles that start ij. If I want a 3 cycle where I and j come in the reverse order, so j goes to I rather than I goes to j, I can do, because this is I, j, a squared. And if I have a 3 cycle that only contains I and then 2 different elements, this I can get as ijb times ija squared. Yeah, I think. And if I have a free cycle that contains j and not I, and this one I can get as ijb squared ija. And if I get a free cycle that doesn't contain either of I and j, what can I do? Apparently I can do ij squared ijc ijb squared ja. Yes, I can get a new free cycle. So can I get everything?
Yeah.
Why?
Because you can get any free cycle.
And then? And then I have lemma 10(8), which says that if I have all three cycles, then I've got everything. Okay. Okay. Why are you doing this? Let n be a normal subgroup. Of an. And n is greater than or equal to 3. If n contains a 3 cycle, then it has to be the whole group. It can't be one thing. That has a really simple proof.
It beats my head, however.
Why? So what we kind of want is, what we already know is if I get ija for all different a and two fixed I and j, then if I get all these 3 cycles, then the subgroup will be the whole of an. Okay, and I only have one free cycle. So n contains, I'll call them ijb. No, I'll call them ija. So this is some free cycle that is in the subgroup. Okay. Now what I want is that I and j stay, if I and j stay the same, but I can replace a with b for any, and I can take any b in an other than I and j. Okay. I have one 3 cycle. I know I have one 3 cycle, but I would like to have all these 3 cycles that start with the same 2 numbers. Because if I have all these 3 cycles that start with the same 2 numbers, then by lemma 10.8.5, got the whole group A.
So A is specific.
Yeah, so A is specific now, but B will be, but I want all different B to appear. Okay, so let B be any thing, any number between 1 and n, other than I and j. Okay, so ija, I know I have. It's a subgroup, so ija squared, I also have. Agreed? So now, if I do AB, ij, that I don't have, maybe. I don't know. I don't know whether that's in N. Well, maybe it's not in N, I don't know. But if I do the same thing, inverse, on the other side, that's in N. Because N is a normal subgroup. Okay? I have ija squared because it's a subgroup, and a normal subgroup, if you times it with some element of G, this is an even permutation. I times it by something from the right, and it's inverse from the right, I get again something in the normal subgroup. That's part of the definition. Well, that's one of the conditions for a group subgroup to be normal. So this is in M. Well, now you have to work it out. What this is. Yeah, it is indeed in the book. So apparently this thing is equal to IJB, and I'm sure I've checked it. But, so where does I go? I goes to J, J goes to I, goes to J. So I goes to J, that's good. Where does J go? J goes to I, goes to A, goes to B, so J goes to B, that's good. Where does B go? B goes to A, goes to J, goes to I, so B goes to I, that's good. And where does A go? No. Yeah, where does A go? A goes to B, back to A, so A goes to A. So yeah. Well, that's kind of it, right? So that's what we wanted, and now by 10.8.5. And it is, well, I have all the 3 cycles, ij something else. And it's a subgroup, so it also contains all the products, and all the products are the group. Yeah. So what remains is to show that, if you want to show that that it's not simple. So if I take something that's not just the identity, and it's a normal subgroup of AN, then it has to contain a 3 cycle. and N contains a free cycle. And combined with this, that's going to prove that there are no normal subgroups other than the identity. And if I get a normal subgroup, either it's the identity, and that, well, that is a normal subgroup, or it is not the identity, but then it contains a free cycle. But if it contains a free cycle, then it's the whole A. And that's kind of the end of showing that. But it's simple, but this proof is not easy, so we'll leave it for tomorrow. Any questions? Come on.